All right, so welcome. This is our last lecture, and we want to continue with what we did last week, where we started with matrix decomposition and we spoke of uh, singular or single value decomposition. All right, now we want to continue by adding PCA, okay, PCA, and we'll have a practical scenario where we'll have an example and we'll look at the theory behind it. Now, last week we saw that when you have a matrix, which we said a matrix are used to store our data, we said we can decompose this matrix, and we saw last 2 weeks that we have the eigen decomposition. With eigen decomposition, we said we have three different components, and we said we have the rotation, then we also have stretching, we have rotation again. So we have two rotations and one stretching. Last week also we saw the same thing with the matrix decomposition. And with the matrix decomposition, we also saw that we can decompose the matrix also into three components, still with two rotations and one stretcher. But last week tutorial, we saw that whether the matrix you want to decompose is square or not, we can still go ahead to decompose it because we were able to find a way to convert our matrix into a square matrix by multiplying it with the transpose. Then we also saw that we can also convert this matrix to a symmetric matrix, and symmetric matrices are very, very important because that is one criteria that is needed in our matrix decomposition. We saw this last week, and when we do the decomposition, we saw that the first one, or the first decomposition, which let me have our matrix. So let's assume this is a matrix. When we decompose it, we saw we have some u, then our sigma, then our v transpose. Now last week we saw this is made up of bases, autonomous bases. This one too is also made up of our eigen values, right? Okay. Then this one too is also made up of another basis, okay? But that is the inverse of our this. And we saw that these ones are actually our eigenvectors, okay? Our eigenvectors. And when we transpose it, we find the inverse. This is what we will get. And these are our eigenvalues. Now, this is what we were going to use, okay, to be able to build on the principal component analysis. So let's proceed. Now, I want to congratulate you all, those of you who are here, okay, for sticking with us till, I mean, this last lecture. You have done well, and I mean, you have to be celebrated. We started almost 76 students, and we are 16 over here. That means over how many? 60 students are off. Okay, 60 students are off. All right, so congratulations, you have done well. All right. So before we come back, let's talk about some applications of the single value decomposition. The first one is creation of latent variables. Now, this is something that is very, very important. Okay, anytime you have data, one of the things that data scientists they actually spend time is hidden relationship, and this, if you don't have the skills, you look at the data and there's no way you'll be able to come up with any meaningful information from it. Any data that you see is having a hidden relationship, hidden information. You can only find this using single value decomposition, which is, and with single value decomposition, you can create latent variables. These latent variables, they enable you to be able to find this hidden relationship. And with this hidden relationship, you'll be able to conclude, you'll be able to, decide the outcome of your data, the outcome of your data. Now, one of the challenges we are having in Africa, in our country, is we don't have data. Our data is scarce. Okay, and sometimes anytime we have data, the interpretation becomes problem. That is something I always tell my students, that most of the time we rely on spirituality. Charlotte, are you okay? Hello, Charlotte. Okay, we rely on spirituality more than what interpreting of what of data. Okay, so when we have data, we have to find the hidden relationship. That is what is crucial. That is what is important. Okay, so single value decomposition can enable you to achieve that. So those of you, after this, you can take it up, work harder, and discover much from it. So a practical scenario is, how can you predict whether it is raining or not without information on the weather report? They've given you data. And how can you know that it is raining or not? There are two options. You came out from your room, you saw that what the ground was wet. Maybe your friend came to visit you, you saw that your friend was holding what, an umbrella. Or your friend came to visit you without holding an umbrella, you saw that your friend was wet. All these things are information that you can use to be able to what? Understand what is happening. We call these things latent variables. Latent variables. Okay, and with single value decomposition, they are present in the U and the V. The U and the V contains this. Now, this type of variables allow us to reduce dimensionality of data. So we'll talk about this. So let's proceed. The next thing is approximation of matrix. Now we saw this. Sorry, we see this in PCA. Okay, when we try to reduce the dimension of a matrix. Now, when you have data, remember that when you are dealing with data, some data are not necessary. If I say they are not significant, they are not important. When you use them in your model, we say they introduce something known as what? Noise. Okay, known as noise. They are not relevant. And that is one crucial thing data scientists find time to work on, because you have the data, they give you the data, you are now going to work with it. But do you need all the features? Some features are not important, they are not significant. So you need to be able to remove the less significant features and pay attention to the more important features. This is where we talk about reduction, dimensionality, where you have your matrix, you pay attention to the important ones and remove the unimportant ones. If I say remove unimportant one, I'm talking about the features. So we can remove data or information that is not relevant to what we are trying to do. When it happens like that, we condense this. Okay, so this one gives us an approximation. It gives us an approximation, and this helps. Although we are condensing or we are removing the irrelevant ones out, we are approximating our data, but it's able to work efficiently. And that is what principal component analysis relies on. So we've seen the application of SVD, creating of latent variables, and also um, creating of what? Matrix approximation. So the next thing is we can create a simple recommendation system using SVD. We are going to go through it theoretically, as I said. I'll share the notebook with you guys on the platform so you can download it and go through yourself. So let's assume we have 6 different songs that users have rated according to their preferences. And we have 8 users who did the rating. So let's look at our data. So this is our data, which is in a matrix form. Now, there are 6 songs. So we have song 1, song 2, all the way to song 5. Okay, and these are our users. They have done their rating. If you look at some of them they rated some of them good, others bad. Now, there are a lot of information over here. Remember, one, we don't know the genre of the song. We don't know the genre of the song. That means they told us somebody we should rate, the song, right? But one hidden thing is that we don't know the genre of the song. So there's nothing we can say over here. They said we should rate the song. Is it hip life? Is it high life? Is it gospel? Whatever, we have no idea. But we just ask them to rate the song. Now, they have done that. We've gotten it. We want to be able to find out the hidden or the latent, variables in this data. How do you do that? You are going to apply SVD. Now, first, we need to decompose our variable, sorry, our matrix into our three individual components, which is our U, our sigma, and our V. This we did it last week. If you look at our matrix, let's go back. You tell me the dimension here is 8, here too is 6. So our is going to be what? 8 by 6, right? So that is what we see over here. Now, in order for us to be able to decompose it, we have something known as the full version of, and also we have also the reduced version. Now, the full version means we are using everything, but the reduced version, you're going to pay attention to the column space. Now, the column space, we are talking about the columns that are independent. This one also goes down to the same thing, like paying attention to the relevant one and neglecting the irrelevant one. So here, let's assume we are using the full version. Okay. So when we do the decomposition, our U is going to be of this dimension, our sigma is going to be of this dimension, and our T is going to be this dimension. Now remember, we said the hidden variables or the latent variables will be present in our U and what? Our V. All right. So now how do you calculate the U? Now this, last time we learned how to do the calculation, right? We learned how to do the calculation. This, as you can see over here, are used by, it has been, a code has been written, okay, to be able to get it out. That's why I wanted to show you guys how to do that, but I'll share the slides. So when you take, I'll share the notebook. When you take the notebook, can you go through my code and you understand it. So here, when we do the decomposition, this is the value of our U. Code has been written, and with the code, this is what the value that we had for U. Last time we learned how to do the calculation for the U, right? Now this is also the calculation for a V. These values, when you do the code, or when you write the code, this is what will come out. Then this is what you also get when you get a sigma. Now if you look at it, these are values that we have. Now how do we use this to be able to, get the latent information or variable that are hidden? Now, if you look at our sigma, let's look at it. We saw this last week, that the sigma, the first one will be greater than the second one all the way to the end. So let's go back and let's look at it. If you look at this, the first one, this is the second one, this is the third one. If you look at it, have you seen? Now, it is decreasing in that order. Now, if you look at it, you can also see that it's only 1, 2, 3, 4, 5, 6. This part is not included, right? Now, remember I said initially that we have the reduced one, we also have the full one. Now, this we are using the full version. That's why you see these zeros over here. Okay, but they don't contain any data. If you're using the reduced one, we remove this. We are going to remove this. Now, when you remove this, it's going to affect this and also that, because I said initially that these data that you see over here, which is the features that you see over here, some of them are irrelevant. They are not going to, help us. So we need to take them out, or else it will be like a noise in our data. Okay, so now now that we know our sigma, what are they trying to, imply? Okay, or what are we going to use these ones for? This sigma that you see, we call them variance. We see them again in PCA, okay, which will create something known as what? The covariance matrix. When you talk about the variance, we are talking about the spread of the data. Okay, when you talk about the spread of data, it means the data, they are independent, they don't depend on each other. So the higher the value, the bigger the spread. That means these data, they are independent, but the lower the value, it means the data, they have similar, they have some form of similarity, and that is what we don't want. So what we want to do is to remove data that's, depend on each other. So in matrix, what we are interested in is, we are interested in what? Linear independency, not linear dependency in vectors. So here, if you look at this, you will see that this is having the highest spread, followed by this, followed by that, followed by that, followed by that. Okay. So in PCA, we can pick maybe the first three and leave the rest because their values are quite high enough for us. So we can say, okay, because these values are quite enough for us, we can use it to approximate our matrix because they represent a higher spread as compared to the others. Now, if we sum, so let's go on to sum this. If we sum our individual eigen values, this is what we are going to get. We'll get, this is the value that we are going to get. Now, in machine learning, we call something information theory, which we'll talk about it the next time the next intention, okay, which is very, very important. Now, from information theory, normally talks about the total energy of our system. So if we sum all the eigenvalues, we say that the energy for our system can be calculated as this. Okay. Now, if you need about 95% of this energy, it means the first three can provide that, and we can leave the rest. The total energy we had 350 dot something. Now, if I want to consider about 95%, it means I can pay attention to the first three, neglecting that because they contribute much than the rest. So what am I doing over here? I'm approximating. So we are going to approximate. All right. So we are going to pick the first three and replace the rest with zeros because they are not, irrelevant. Okay. So they are irrelevant. So when it happens like that, what is going to be the value for U? What is going to be the value for V? What is going to be the value of the V transpose? So this is our new value. The rest all goes to zero. So we are approximating our matrix to these three values because they have the highest variance, the highest spread. Then what we have done is we have reduced our matrix to three. And that is what they call it dimensionality reduction. The last three we said they are irrelevant. So let's pay attention to the first three because that is what we can use. So we have reduced it. That is matrix approximation. There are certain algorithms that work better. For example, clustering algorithm works better in lower dimension. So it's better to pay attention and remove all irrelevant features so that you have the relevant ones so that your algorithm be able to work on it. You see, I've highlighted this point. It's very, very important that working with a model with all of the available information does not guarantee good results. Why? Because your model is going to learn noise. It's only noise that is going to learn. It's going to be noise, 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 noise. We don't want that. So what you have to do is you pay attention, you reduce to the level that it can capture the entire data so that you can do away with irrelevant data. Right. So with our reduced version, this is what we are getting. So this is our matrix. We started with this. Now, because we have reduced this to this, it's going to affect the rest, as you can see. So we have reduced our matrix to this, as you can see. Now the U has been affected. How many columns do you have? You have three. Okay. The V2 has also been affected. How many rows do you have? We have three. So it has truncated the irrelevant ones out, leaving the relevant ones so that we're able to use it to be able to find out our hidden um, variables. So as you can see over here, we truncate. So we pay attention to the first three. Okay. Then the same thing goes with our sigma and also the V. All right. So this is our U now. So look at our U. If you look at it, you saw we have a lot of context. Let's go back so that you see the U. So when I come back, you see that we have removed unnecessary things and paying attention. So look at our U now. This is the U. How many features from context 1 all the way to context 8? Now, when we did the dimensionality reduction, we have approximated our matrix to 3 features now. And this contains much information. Contains much information. Now, when you plot this, so this, you see, and the interesting thing is that if you look at the first one, if you look at the dimension, how many features did we have? We had almost like, I think 8 or 7 features, right? So that one will be what in the 7th dimension. But now, since we're able to represent or approximate that matrix using 3 dimension, now plotting it becomes what? Much easier. And all these things I did in the notebook. So you see. So once I do the plot, you see that, wow, some of them are clustering together. So if you look at it, user 0 and user 7, they are together. If you look at user 1, user 5, user 2, they are also together. And user 4, user 5, user 3, they are also somehow together. So this tells you something. Now, there are a lot of things that you can say over here, but please, depending on the problem you are solving, will let you know the interpretation to give. Depending on the problem you are solving, will let you know the interpretation to give. So we have 8 users. When we did a dimensionality reduction, we have 3 clusters. What can you say? One, is it because they did a rating, these 3 clusters, they love the same music? Or is it because they prefer the same genre? These are questions that you ask depending on the problem. So the problem you are solving will let you know your interpretation to give based on when you plot your approximated matrix. So we could segment based on their music taste, applying clustering algorithms you can see. So in this case, a higher dimensionality with the singular values that differ more. So all the explanation I've given, when you read the slides, you will see that. Okay. All right. So this is the clustering as you saw. I think okay, so this one is quite different. So let me do the proper. So this is different from this. Then this one too is different. So I think I made a mistake initially. All right. So this is different. Then this guy is also different. Okay. This guy is also different. This guy also was different. All right. So different. So we have how many clusters? 1, 2, 3, 4, 5. So that tells you that this guy, this one, user 4, they are different from each other, from the rest. So let's go and look at the table. All right. So with this, as I said, depending on the problem you are solving, will lead you into your interpretation. This is where the thinking comes in. Okay, you start thinking what is actually happening. So user 0 and user 7, does it mean that they love the same music or they love the same genre? Or maybe they're from the same country that they are choosing the same song, or the song is in their. So all these things, will play a role, okay, to your interpretation, so that we're able to understand the hidden variables in the data. Okay. Now, we will not be doing any training, but in machine learning, we do training a lot. So training means you're finding configuration for a set of numbers or parameters. So let's assume I have an equation. Y is equal to um, mx, right, plus b. Okay. So when we say you are training in machine learning, you are looking for a configuration, these parameters, the m and the b, that will map this to this. Okay. So that will map this to that. So this is an equation, and we are mapping this our features to our target. But this is controlled by some parameters, which is the m and the b. Can we let the computer keep on adjusting the m and the b to be able to do the proper map? If I say proper mapping, be able to, get close to the mapping that we are interested in. So when it happens like that, we say you are training. You are doing training. Okay. So now when you are training, you need to find a way to use less of these. Okay, we call them features. Now, if you have more features, your model will learn noise. So how do we do it? That is where the dimensionality reduction comes in. So here, you are going to reduce the columns. Now, if you have your data, we saw this. Okay. Now, the columns represent your dimension, right? So if you have columns almost like 30, that means you are in the what? In the 30th dimension. Now, what all these dimensions, all these columns, would they play a crucial role? Some of them are irrelevant, they are not significant. So what can we do? We can take them out. We can remove them. Okay. So when you do that in machine learning, we call it what? Dimensionality or reduction. Okay, and that is something that deep learning has been able to solve. Okay, we call it case of dimensionality. In machine learning, the higher the dimension, the more the model they learn noise. But in deep learning they don't care. They can learn at whatever dimension that you give to them. They can still learn. Okay, we'll talk about this. All right. So in order for our model to be able to learn properly, we need to move from what? A higher dimension space to what? To a lower one. Thus reducing the complexity of the problem. So we move from a higher dimension to a lower dimension, okay, so that we can reduce the complexity of the problem. All right. So if you look at the VT also, it's also what? Reduce it. So here we have what? 3, then what? 5. Okay, we have reduced it, so we'll be able to work with it properly. Now when you plot this, you can also see that, hey, there's another classroom over here. I believe this one I get it correct. These ones are also together. I'm sure I'm correct. Then I think these two also together, and this one too has also been isolated. What can you say? Now, is this one talking about the genre of the music? Is it hip hop? Would this one be hip hop and this one would be whatever? So you see, the way we have reduced our matrix, we now be able to now talk to ourselves and say, okay, what am I getting? So we saw that the U and the V is able to provide us with those what information, the hidden, variables or the latent variables, able to provide all these things. Once you plot it, you can obtain much data. This is just a practical scenario which is not related to any real world, but your problem, any domain that you are coming from, you pay attention and be able to what? Make meaning from it. This is what makes you a machine learning engineer or a data scientist. You have done the reduction, you have plotted, or you have your graph. What can you say when you look at the graph? What inference can you give when you look at it? These are things that you pay attention to and be able to, draw conclusion. So by computing U and the V transpose, we can find hidden relationship with data represented by what? Latent variables. This relationship can be leveraged on to train what? Your algorithm. So you see how we started, we decompose, okay, then we pay attention to our U and the VT, and but we use the sigma to be able to what? Reduce the U and the VT. We use the sigma to be able to reduce our U and the VT. So once you've done the reduction, then we are good to go. That okay, what is hidden in the data? Then you now start asking yourself questions. Once we're able to achieve that, we can now use the algorithm, and the algorithm will be able to what? Leverage on that to train. Okay, all right. Okay, so let's jump into PCA. But before we do that, we saw that matrix is linear transformation. Now, I believe you all know when you talk about matrix, when you are talking to your friends now, you're able to tell them, oh, these matrices are all linear transformation. So when you're dealing with machine learning, remember we are transforming vector from one space to another. Okay, you now understand it. So when somebody do any machine learning project, you can look at a person who'll be smiling because guess what? You transforming from one space to another. So when you multiply a vector by a matrix, you are moving these vectors. You are taking it from one space to another space or from one space to a different space altogether. It's possible you can be in what? In two dimension and do the transformation, okay, to three dimension. It's possible. Okay, you can move from from one dimension to another different dimension or the same dimension, okay, to the same dimension. It's possible. Okay, so in machine learning, this is what is happening. We are moving these vectors from one space to another, and it's being done by what? By a matrix. All right. So what is the role that these things plays in PCA? So let's talk about this. We also have another example, and you see the importance of PCA. Those of you who will do your projects, I expect more from you. Tell us more. Okay, don't come and explain PCA because we are treating it. Tell us the application. I mean, with regard to your project. Okay, and try to explain uh, your results to us. So PCA has, I mean, assumed an increasing role in a wide range of applications, including machine learning expert, image compression or image processing. They used to compress image, okay, speech recognition, face recognition, data mining, semantics, and what? Informatics. You see the role. So we are seeing it role in various domains. All right. So PCA used to what? Simplify data by looking for linear or what? Affine relationship between measurement of different data points. I've explained all this already, that they, you have your data, but some of the features are dependent. They are linearly dependent. Can you remove the linearly dependent ones and focus on the linearly independent ones? But that one is what, I mean, contains the hidden variables. So the key idea behind PCA is that the singular vector, which is our U, associated with the larger singular values, which is our sigma, represent important correlation in the data, while those with the smaller values indicate relatively important, I mean, relatively unimportant. So we saw our U, then we have our sigma here, then also have our VT. Now this is the eigen values and this is the eigen vector. Then we find the inverse of this to get our VT. Now this one will give us real values, and from PCA we are going to pay attention to the vectors over here that are having higher values for the eigenvalues. And as you saw when we did the singular value decomposition. So those with the higher values, that's what we are going to pay attention to in our U so that we neglect the unimportant ones. So what is happening? Now, when we do that, we are doing something as well projecting. So we are projecting the data onto something as well principal component. Now, the principal component these are the vectors that are important. Remember, if you look at the previous example, we had the matrix, it was 8 by what? 6, right? But at the end, we saw that the sigma now, the dimension of the sigma has now changed to 3 by 3, right? And it even affected the u. If I remember, or if I recall, the u was 6 by 3, no, 8 by 3, sorry. It was 8 by 3, 8 by 3, and the vt was, I think, 6 by 3. Yes. So this, we have decomposed it now to a lower dimension. But what are we doing? We are doing something known as what? Projecting. We are projecting. Projecting, what are we projecting? It's the same thing like God. We are transforming. We are transforming the vector from one space to another. That is what is happening over here. So we are projecting the data onto a principal component. Okay, that is going to yield an effective dimensionality reduction algorithm. Okay, so what is happening here, as I've already explained, is we start with a matrix with a higher dimension. We want to find the principal component, meaning the important features that are needed. Now, once we do that, we cannot approximate this matrix to a form or to a lower dimension that can capture all the features we have in the larger matrix. That is what we're actually doing. So what principal component analysis is doing is that, as I said, it's just doing data projection into a new set of axes or a chain of base that occurs via what? Linear transformation. So what explanation I'm giving over here, we are transforming it from one space to another. Okay, but at the end, we are going to get a new axis or a new base. Okay, all these things I believe you are now, or you understand, because you've done it already. All right. So once you do your transformation, you now get something as well, your principal axis. Okay, your principal axis. Now your principal axis is where we project the data and get the so-called principal component. The principal component are the sigma values that we are going to pay attention to. This is what we are going to use to be able to transform all the matrices. So enough of the talking. So let's proceed to a practical example. Okay. So before we come to this, okay. So so from here, now when we talk about, transforming or moving from one dimension to another, we use the word axis. So we are talking about orthogonal vectors, and you guys already know that the U is, they are orthogonal. Okay, we saw that they are orthonormal basis. Orthonormal means they are orthogonal in nature, right? Then we also saw that it's also symmetric. Okay, that means it has to be symmetric. It has to be symmetric, right? All this, we saw it when we were dealing with the matrix decomposition. So we are going to apply the same thing over here. Then also say that when you have any matrix at all, we can create a symmetric matrix out of it by multiplying by what? By transpose. And once we do that, we be able to create a symmetric and also come out with a square matrix. We did this. So with the same idea is what we are bringing over here. But there's something that we have to pay attention to, which is new, known as the variance. We saw the variance in the SVD. But in PCA, we call it the covariance. Covariance. What is covariance? Now, when you talk about covariance, there are features we have in our data that changes together. That means if one is increasing, the other one is increasing. If one is decreasing, the other one is decreasing. And these ones, we don't want them. Okay, so we say that in vectors, they are linearly or dependent. And we don't want linearly dependent. We want to linearly what? Independent. So how do we do that? We need to find a way to remove these ones. And that's once we're able to remove it, we now have something known as what? A covariance matrix. A covariance matrix. Okay, so the covariance matrix is symmetric, positive. Its eigenvalues also positive and eigenvalues are perpendicular. That means they are orthogonal. That means they are all linearly what? Independent. Once we're able to get our covariance matrix, we are done. We have removed all irrelevant data from our data set. Now, what is left are the important ones, the linearly independent ones. And with this, we can now go ahead and use it in our algorithm training, whatever you want to do. So let's look at a practical example, which the data that you see over here, I mean, it's not a real life, something that's, I mean, we came up with. Okay. Now, the eigenvalue from the sigma, okay, as you saw, represent a scaling factor that comes from the covariant matrix. Okay, so the largest value will correspond to the highest direction of the variance. Now, I've already explained what the variance is. You said the spread of the data, right? Now, the higher this variance, the better. I mean, our data. We want our data to be, because they will not be dependent. Okay, so when you have a high value for the eigenvalue, it means our variance will be high. Okay, and that corresponding eigenvector is what is going to be used for our principal component. I will explain it, you understand it later on. Okay, so let's look at this data. Now, if you look at this, given this data which represent features of users for online casino games, so people, I mean, betting guys, I don't know whether some of you have been betting, but so here we have users total bet value, total 3,000 times. He has won zero. The total days play for and average whatever. So this data that we have. Now, this data, there are a lot of hidden variables here. But by you looking at it, maybe it will not be clear enough. Okay. But if we can decompose this and bring it to a lower dimension, we remove all irrelevant stuff out, we'll be able to get, I mean, the hidden variables and the hidden data, I mean, or the hidden variables in this. So how do you do that? Let's start. So we are going to use PCA. So the first thing is to transform this data into our with our principal component analysis. So what we are going to do is we need to find out to calculate the covariance matrix. And I said the covariance matrix, all we need is to find a way to remove all the dependent features so that we have all the independent features to work with. So first, we need to create or calculate the mean, and also calculate the standard deviation. Now, the mean and standard deviation, this is things that we can do, but we are going to calculate it column wise. So if you take the first column, we find the mean, we find the standard deviation. We take the second column, or if we take the total one column, we find the mean, find the standard deviation. We take this one to the same thing all the way to this. Once we do that, we're now going to do something as a standardization. We're going to standardize our data. This is not normalization. We are not normalizing here, we are standardizing it. So we pick each column, then each column is having a mean and standard deviation. So we subtract the mean from the example, then we divide by the standard deviation. So here, when you come back here, let's assume we had the mean to be, let's say, 5. Let's assume the mean is 5,000, okay? And the standard deviation, let's say 400, okay? Now what I'll do is I'll take 3,000, then subtract the mean, which is 5,000. Then I'll divide everything by my standard deviation, which is what? 400. You get it? So that is that. So we are going to do it for each column, and this we have. You can write script to do all these things. Okay, you can write script to do all these things. So when you do that, this is what you will get. So this is what you get. So here we have done the calculation. So if you look at this, we have the mean, we have the standard deviation for this, then the mean for that, the standard deviation, the mean, and that. So we've done the calculation for each feature or each column. Once we do this, we do the subtraction. We are going to do subtraction. So here we will standardize it. So we subtract and divide by the mean. If you have calculator, you can try any of them and you see that this is what we are going to get. So these are standardized data. We have standardized the data now. So in machine learning, we say you are centering it. You want to center the data. You are not normalizing. You are centering your data. Okay. So now that we have done that, the next thing is we now get back to our matrix now. So we put everything in a big matrix, which we have so let's go and look at it. So here 1, 2, 3, 4, 5. All right. So here we have 1, 2, 3, 4, 5. Right. Then we also have our users. User 1, okay, user 2, user 3, user 4, user 5, 6, 7, 8. Now, when you are dealing with principal component analysis, you can use any matrix decomposition. All right. So you can use the eigen decomposition. You can use the eigen decomposition. You can also use the SVD. You can use any of them in your PCA. Okay, so your PCA, you can use any of them, the eigen and also the single value decomposition. You can use any of them. Okay. Okay. Now, what do? You remember we said initially that we have to create what? A symmetric one. So in you creating the covariance matrix, we have to make sure that our matrix becomes symmetric. And all these things, you know it already. What do? We have to multiply a matrix by a transpose, right? And this is the transpose of this. So when you multiply, we end up getting our symmetric. Okay, we end up getting our symmetric. So this is our symmetric matrix. Now we need a covariance. To get a covariance matrix also, we divide it by the number of examples. So how many examples do you have in our data? 8. So here we multiply our matrix by a transpose and we divide each entry by the number of examples. So as you can see, that is what we've done over here. So if you look at it, you see this is symmetric. This is our diagonal, and when you flip it, it's still the same thing. So we now have our covariance matrix now. Now that we have our covariance matrix, we are good to go. We have removed all unnecessary things. So now that we have this, the next thing is to decompose it. We have our covariance matrix. We have removed all irrelevant. So let's try to decompose it. We are going to use the eigen decomposition approach, where we are going to split it into this. Right? So this is going to be an eigenvector, eigenvalue, and this is the inverse. So if you go on to do that, this is what you are getting. Now this script has already been written to do that. And in NumPy can do that. So once you get this, this is our P, which is our vector, eigenvector. So this is our eigenvector. Now this is where we are going to find our principal axis, but we don't know which axis we are going to use. We don't know which axis we are going to use. We can only get this axis from the sigma, which is the eigenvalue. This. We've gotten our principal axis. Sorry, we've gotten our eigenvectors, which is the P. And once we know our P, we can go ahead to find this, right? Now we can find this. It's not a big problem, but we need our principal component. To get our principal component, we need this guy to be able to help us do that. And remember we said the sigma, the higher the value of this, the more or the higher the variance. And we see that this is what is important, so that we see that they are not dependent. So that we see that the sigma, the higher the value of this, the more or the higher the variance. And we see that this is what is important, so that we see that they are not dependent. So that we see that they are not dependent. So that we see that they are not dependent. So that we see that they are not dependent. So that we see that they are not dependent. So that we see that they are So let's also find out our sigma. So let's look at our sigma. If you look at it, you see the values in that decreasing order. So if this one is your sigma 1, sigma 2, they are decreasing, which agrees to what you've been seeing so far. Now these values are what are used to explain our variance. So we are going to do the same thing we did in when we were doing the SVD, where we will sum our values. So let's sum our values. If you sum our values, when you sum our values, when you sum our values, you are going to get a little bit about 5. Okay, so I say approximately what? You got to 5. Now, how do you know the variance that is, present? Okay, if I say the variance, the hidden data or the hidden variables present. And that one, as I said, is can be done by what? By the eigenvalue. So we want to find out how much each eigenvalue explain the variance. Okay, the hidden data, how much each value is going to explain it. So how do you do that? If you do this calculation, how do you do the calculation? Excuse me. Now, when you take each, uh, when you take this, what we are going to do is the total is 5, right? So we are going to have 2.29 divided by what? Our 5. Then times what percentage are we using? Okay, so we should use 50%. Sorry, we should use come in a minute. We use can find out. Okay, let's use 100%. Let's see whether it will work. Okay, so let me do the calculation here and let's find out. All right, so we have 2.29 divided by 5 times 100. Okay, you can also do it to confirm. Okay, you can also do it to confirm. Uh, so 2.29 divided by 5 times 100. All right, which is 45.8. Okay, which approximately 46. So that is correct. Then we do the same thing for that. You do the same thing for that. Now, if you look at it, we go back to our eigenvalue. You will see that these three, okay, are the ones having the highest score. These ones, they are less significant. That means we are going to pay attention to the first three. Then we will not leave this one. Okay. So that's the same thing we are going to do. So you pay attention to the first three, which is the PC1, PC2, and PC3. So these ones becomes your what? Your principal component. Okay, the principal component. So the two component PC1, PC2 explains 76 of the variable. So we pick the two largest. Even here, they even pick the two. All right, so we can pick the two so that we leave this because this one is, explaining 76% of our data, which is quite a lot. So we can pick the first two. So our principal component is going to be the PC1 and the PC2. So when you go to the eigenvector, then it's going to be this and that. These are going to be our principal. So this is where we are going to do the projection on. How do you do the projection? We see it. So now this is our PT, truncated PT. So we pick these two. So these are the principal, component. These are the ones that we are interested in, the principal component. All right. So now that we have this, we need to find linear combination. Remember, we did this. We have a vector, and it asks you to find a linear combination where you say what C1 is equal to U1 plus C2 is equal to U2 plus C3 is equal to U3. You see, so you are finding a linear combination, the same thing as what we are doing over here. Now, you've been able to find our principal components now. So what do we do? Just a matter of we are just, having, because if you look at the total bed value, that is a whole vector. Okay, that's a vector. The total one is another vector, this one to another vector, this one to another vector, this to another vector. So what are we saying? What we are saying here is that these scalars, okay, the scalars in front, okay, they are the one that is stretching or shrinking. All right, so for us to be able to get our transformation, it's just a matter of what? Linear combination. So we can express our individual features using the principal component. That's why we say what? You are moving from what? One dimension to another, or from one space to what? To another. The same thing with the PC2. We can also do the same thing. So you see, we have our data now, and now we'll be able to reduce it to a lower or a low dimension and representing it with just few of this. So what have we done here? We're able to transform our version of the scale data with our matrices. So our new reduce now is our new data, okay, which is the new transformation multiplying by this, and this is our approximated matrix. Now let's go and look at it. So here, if you look at the dimension 1, 2, 3, 4, 5, which is what? 5 by what? By 2. Okay, so these are what? Our principal components. So we are transforming it. Okay, we transform our matrix given to us towards a new space now. To a new space now. Okay, so that is the whole idea about PCA. Okay, first you work hard, get your covariance. Once you get your covariance, you can go on to decompose this covariance matrix. Once you get your covariance matrix, you decompose it. Then once you decompose it, you look for your eigenvalues. Then look for the significant ones. You use that one. So if it is only one, you pay attention to one. If it is only two, you also pay attention to two. If it is only three, you also pay attention to the three. Then you use that one to be able to reduce your matrix to a low or a lower one. Okay. Yeah. So this is that. So this is our component. As you can see, you've already seen it over there. Okay. So these are our components now. Okay. So these components are called the latent or the hidden variables. Okay. Relationships that are hidden in the data and the result of what? Of linear combination. Now, the reason why here, this, okay, as I said earlier on, the hidden data can be anything. It can be anything. Okay, it can be anything. So it is up to you, because this is just I just pick a random, sorry, redundant data, and I'll just explain it. It can be anything. So it's up to you to look at what these hidden variables or these latent variables represent. Okay, because once you're able to do the decomposition and reduce it to a lower dimension, you're able to get your principal component out. What do they represent? Your data. If you are dealing with breast cancer data, what do they represent? If you are dealing with malware, security, whatever, what they represent? If you are dealing with image, what? So it is up to you, the data or the machine learning engineer or the data scientist, to be able to figure these things out. And this is where your thinking comes in. This is where you have to stare at your data, look at it, ask yourself a lot of questions, that what is this trying to tell me? And mind you, some of you agree with me that anything that is happening in this world, whether it's from betting, whatever, these are all data. People look at it and be able to get the hidden or the latent variable out. Once they do that, they're able to make inference. And you think that this guy is smart. He's not smart. He's just looking at the data and making inference. Those of you who are in Ghana here, remember during the election, last year's election, right? Last year's election, is it last year or last 2 years? Yeah, last year's election where uh, there's this guy, I've forgotten his name. He came out with some poll and he was able to come out that this party is going to win. Mind you, you go in, you look at it that he might use some of these things, right? He may have used some of these things. Okay, so that is that. Okay, so any question? Any question?